Now have the pleasure of doing 16-4, the area of a circle. This may be one of my favorite lessons that we do all year, so I'm really excited about this. Hope you are too. Okay, so we're going to start similar to how we started 16-3. And again, I don't know if you have these circles drawn in here. If not, go ahead and construct them or draw them carefully about the same size. And then fill them in the same way with your regular polygons. You've got your equilateral triangle, you've got your square, pentagon, hexagon, and an octagon. And what we're seeing here is that the area of a circle is the limit of the area of inscribed regular polygons. In other words, as the number of sides of the regular polygon increases, what happens to the area of the regular polygon? It gets closer to what the area is of the circle. And by limit, we're basically saying as the number of sides increases towards infinity, then the perimeter, or I'm sorry, the area, excuse me, of the regular polygon approaches or becomes the area of the circle. Much like what we saw yesterday with the perimeter to the circumference. Okay, so you all, I know, unofficially, it's going to be official now, know that the area of a circle is the formula pi r squared, where r is the radius. Okay, we're actually going to prove that, and you're going to love this. Okay, so we know that as the number of sides n approaches infinity, we learned in 16.3 that the perimeter approaches the circumference. Okay, and the apothem, remember what the apothem is. It's from the center of the circle down like that, or down like that, or down like that. Well, what's that going to become as the number of sides increases? Isn't it going to become basically the same as the radius, right? As like these sides become closer and closer to the circle, the apothem is going to become the same as the radius. Okay, and we know the formula for the area of a regular polygon is 1/2 apothem times perimeter. Well, that's going to become area equals 1/2. Apothem is becoming the radius, and the perimeter is becoming the circumference. So it's 1/2 RC. Well, remember, circumference is the same as what? 2 pi r. Do the multiplication. 1/2 times 2 becomes 1. R times r is r squared. We're left with pi r squared. How about that? Okay, so area formulas. The area of a circle, area equals pi r squared. For regular polygon, one area equals 1/2 apothem times perimeter. All right, now we're going to do a bunch of practice problems. And again, I really want you to try these on your own. So pause the video and then watch me kind of go through it. All right, so pause and try the first one. Okay, find the circumference and area of a circle with a diameter of 12. Okay, so we know the diameter is 12. Think about what formula you're going to want to use to get the circumference. And obviously, if we have the diameter, we're going to want to use pi times d. And yeah, that's pretty simple, isn't it? Yeah, just pi times 12 or 12 pi. Okay, what's the formula for the area? If I have the diameter, ooh, we have a formula that's pi r squared. Oh, but I have the diameter. And the diameter is double the radius. That means the radius is 6. So 6 squared is 36. So it's 36 pi. Notice here again how I wrote out the formula. The area of a circle, the circumference. I really want you to get in the habit of doing that. It really helps set the game plan, helps me see kind of what you're doing, and making sure that you really kind of set yourself on a good course. Okay, let's try this one. Find the area of a circle with a circumference of 20 pi. When you do this problem, make sure that you really kind of think about what formulas you need and how you're going to be able to get there. Okay, so I need to find the area of a circle with a circumference of 20 pi. I know the circumference. In order to find the area, I know eventually I'm going to have to use pi r squared. Okay, well, I don't have the radius, but I have the circumference, and I know circumference is equal to 2 pi r. So I can solve for r if I know what c is. So if I do that, I'm basically just plugging in 20 pi for c, and then solving for r. So I divide both sides by 2 pi. The pi's cancel. The 20 and the 2 become a 10 and a 1. So the radius is equal to 10. I then just have to plug in 10 here. So 10 squared is 100, and I get 100 pi. Okay. Two circles have areas of 3 pi and 10 pi. What is the ratio of their areas? Well, if I know their areas, isn't the ratio just going to be 1 divided by the other? Yeah, 3 over 10. Okay, cool. All right, I want you to get your textbook out and look at page 547. We'll look at problem number 6. And basically it says prove the following theorem. And we're not going to prove this like a 2-column proof. We're just going to prove it using, algebra basically and formulas. And what we're trying to prove is that the ratio of the areas of 2 circles is equal to the square of the ratio of their radii. Again, the ratio of the areas of 2 circles is equal to the square of the ratio of their radii. Okay, so go ahead and see if you can think about how you would do that. All right, so I know that area of 1 divided by area of 2 would be the ratio of their areas. Okay, so what I'm trying to show is that that's equal to the square of the ratio of their radii. Well, if the area of 1 over area 2, couldn't I also express that as the pi times r1 squared over pi r sub 2 squared, right? Where this is the radius of the first circle and this is the radius of the second one. Well, the pi's can cancel, right? And so I'd have r1 squared over r2 squared. Couldn't I basically, in a way, kind of factor out the squared and rewrite this as r1 over r2 squared? Isn't that is equal to the square of the ratio of the radii? So I just proved it. Okay. Yes, this stuff is awesome. So we're going to start kind of getting into shaded region problems, and we'll be spending in the next few days on this stuff. But before we get to that, we need to talk about what an annulus or an annulus, and I think you can pronounce it both ways from what I remember. And basically an annulus is an area bounded by 2 concentric circles. So let me kind of show you using the highlighter function kind of what I'm talking about. So the annulus would be the area between this smaller circle and this bigger circle. So let's go back and try that again. It would be kind of like all of this area in here. And I'm not filling the whole thing, but let's see if I can do a little bit more of it. So it's all of that area between those 2 circles, okay? So that's what we're trying to get, okay? So what would be our game plan for that? Let me fill in a little bit more here just because that's how I am. All right, what would our game plan be? And again, coming up and thinking about your game plan first, and then using formulas would be important. Well, basically, if we can figure out the area of the big circle and subtract the area of the small circle, wouldn't that leave us with the yellow area, right? We'd be getting rid of this white part. So yeah, so the one way we would characterize that is with area of the big circle minus the area of the small circle. Okay. How would we characterize that in terms of the formulas we know? And remember, we know the equilateral triangle has side 6. Okay, well, wouldn't it be the area of the big circle would be pi r squared, meaning the big radius, so like this, minus pi r squared, which would be the small radius, the radius of the small circle. So what I'm going to go ahead and do here is actually, well, I'll mark it on this diagram. This is going to get messy, you know it would. Let's go back to the pen. And I'm going to draw in, I wonder if I should do it. Well, yeah, I'll do it here first. I'm going to put that there. And then I'm going to come over here. So that was the apothem, and this is the radius, right? That's supposed to be straight. You know that. And what would this be? This would be a right angle, wouldn't it? What would the degrees here be? Well, if it's a central angle of an equilateral triangle, right? We know that this would be 120 degrees, which means this would be 60. Okay. If that's 90, then we know this angle over here is, you got it, 30. Okay, and we know that this length right here is half of the side, right? 6, because this is obviously a perpendicular bisector. This would be 3. Okay, so how does that help us? Well, we need to know what this is, right, to figure out what little r is, and we need to know what this is to figure out what big R is. Well, we have a 30, 60, 90 triangle, and if the side opposite the 60 is 3, then what would we do to get the side opposite the 30? Remember, we would divide by root 3. So we go 3 divided by root 3. We know we're going to multiply top and bottom by root 3. So we would get, what, 3 root, I hope I said multiply top and bottom by root 3, right, over 3. And then what cancels? The 3's. And we're left with just root 3. So this is root 3. And then we know to get to the hypotenuse, we just double the 30 length, which is root 3. So this would be 2 root 3. Okay. And, you know, if you ever on a diagram don't have enough room, you could always like kind of blow up that triangle right there down here, make it bigger for you, easier to see. Okay, so basically all we have to do is plug in for r squared and for r squared. So 2 root 3 goes there, root 3 goes in there, 2 root 3 squared is 4 times 3, which is 12. So we have 12 pi minus root 3 squared, which is 3 pi, and that gets us 9 pi. Awesome. Okay, find the area of the shaded region. And I'm not sure if it's clear on what you have there, but we have this is a square, and it's got a side of 10. The shaded region is basically the area between the circle and the square. So those 4 spots right there. Okay, so what would your game plan be for this? Well, hopefully you just said it's the area of the square minus the area of the circle. Okay, well, what's the formula for area of a square? Side squared. And what's the area for the circle? Pi r squared. Okay, so what do we not have here? Well, we have everything we need, but we don't have technically what the radius is, right? We know s is 10. But in this case, isn't the radius just going to be half of the side of the square? So it's going to be 5. So if that's the case, we just plug in 5 for r, and we get 100 minus 25 pi. Now, you always want to make sure, like one way of checking this is make sure you don't get a negative area, right? And by the way, 25 times pi, we know is 25 times something less than 4. 25 times 4 would have been 100, and that would have been no good because we can't have an area of 0. So multiplying by something less than 4 knows that we know this is going to be a positive number. Okay, cool. Onward. Our last problem, find the area of the shaded region. Okay, now I don't know if this is clear to you or not, but basically these are kind of quarter circles here. So this is a quarter of a circle and 4 quarters there. Oh, so what would be your formula that you could set up? Area of the square minus the area of the 4 quarter circles. So 4 quarter circles, doesn't that make just a full circle? And what would the area be? It would be of the square, it would be s squared, and then 4 times the area of a quarter circle, which is just 1/4 times pi r squared. So what's the radius? Similar thing here, right? We know that this is going to be half of the side of 10. So and by the way, the 4 times 1/4 just makes 1 pi, or pi. And then we just plug in. And yeah, we get the same answer as we did over here, which should make complete sense to you because we've just kind of turned things around. We've taken these 4 quarters, and instead of it being here like this, we've put it the right angle over here and made it like this. Right there. Okay, So hopefully that's good. We're going to do more on shaded regions. It's kind of a worksheet that normally we would do in class or for homework. We're actually going to do it as lesson videos. I think it's probably a little bit more fun that way and instructive. So we'll have that coming up. But there's your lesson on 16.4. Hope you had fun.